Swayam Prabha. Digital India. Educated India.
Now we will talk about shear center of a section. This is very important in connection with bending of beams. Beams can be made up of cross section of various types. You can have a cross section of the I type, C type, L type. When you try to consider bending of such beams of such cross section, suppose a shear force is acting on the section like this, then you are quite clear that the shear stresses that acts due to V are going to be like this. We will have maximum shear stress near the center of the wave, and then it will gradually reduce in magnitude as we go away from the center portion. Similarly, in the flanges we are going to see maximum shear stress around the junction of the flange and the wave, and it will gradually reduce to 0 there. This stress is also going to reduce to very small magnitude here and there. Similarly, on this side we are going to have shear stresses located or oriented like this, and for this bottom flange it is going to be exactly mirror reflection. So, this is how the shear flows are going to be on the cross section. Now, if you consider a beam of this type of section subjected to a shear force like this, then in that case this is the CG of the cross section. Again you will find that about around this CG we are going to have maximum shear stress, and then it will reduce to small magnitude at the junction of the flange and the wave, and then in the flanges we are going to get shear stresses maximum there, and it is reducing to 0 at this point. On the other side it is going to be like this. For a section of this type, if the shear force is acting parallel to this, then in that case if CG is somewhere there, then we will have maximum shear stress like this, and it will reduce in magnitude to 0 at the bottom fiber, and similarly it is going to reduce from the maximum at the CG to this point, and on the flange we are going to get shear stresses like this. Now, look at this difference. If you consider this type of section, you see that the magnitude of the shear stress acting at this point is same as the magnitude here. Magnitude of the shear stress here is same as the magnitude there. So, therefore, if you now sum up the shear stresses over this portion, you will get some resultant force acting in these directions. Let us say that is F1, and similarly if you sum up the forces for this segment, you are going to get some magnitude which is going to be, let us say, F2, and you will find that for this symmetric section F1 is equal to F2, and therefore, you do not have any net force acting in the horizontal direction. So, what you really have, that if the shear force is acting parallel to the y axis, in this case you find that F1 minus F2 is equal to 0. So, therefore, there is no net force in the horizontal direction, z direction. On the other hand, if you consider this case, here you see that you are going to get some total of this giving rise to a force which is of magnitude equal to let us say F1, and the same force we are going to get here, which is going to be now oriented in the direction opposite, and it is also F1. So, what we find is that we have a force Vx coming out as an internal reaction due to the external force, and that is certainly distributed like this. So, this accounts for that. And now, what you find here, that you have now two forces acting on the flanges, which are going to give rise to resultant force 0 in the horizontal direction, but there is a couple here. There is going to be a couple acting like this, and which will try to rotate the cross section. On the other hand, in this case, since F1 is directed like this, F2 is directed like this, similarly we will have F2 directed like this and F1 directed like this. So, therefore, they are all going to cancel, there is not going to be any rotation here. Same is the picture here, that if I apply a force parallel to the y axis, then in that case my stresses are going to be due to this V is like this, but there is a set of stresses acting on the flange which remains unbalanced. So, there is a net force acting in this direction now, and it is also going to produce some moment. So, we have to see that this moment is not there in the cross section, otherwise it will give rise to rotation of the cross section. And we will show that if the plane of the loading passes through a point of the cross section, typical point on the cross section, then there will not be any rotation of the cross section. So, such a point for the cross section is known as shear center. So, shear center is a point typical for a cross section. If the plane of loading passes through that point, there is not going to be any rotation of the cross section. So, before I go into that, I would like to show you what is going to happen in practice. So, let us now try to consider some demonstration of this phenomena. Now, consider this case. We have a section here, you see it is a C type section. So, I am holding it at this point fixed. Now, if I try to put this is a section, this is one of the axis of symmetry for no doubt, all right, and this is the other axis which is not symmetric. So, therefore, this is one, it has one axis of symmetry. You will find this type of problem more often coming up for sections which has one axis of symmetry or no axis of symmetry. In the case of I section, you have both the axis of symmetry, you do not have this problem, but in a C section like this or L section, in this case you have only one axis of symmetry, and you will have this problem if the loading is parallel to the axis which is not a axis of symmetry. So, let us see that if I now try to put a bending load like this, this is the point through which I am applying the load. You see that if I apply the bending load like this on the cross section, there is no rotation of the cross section. On the other hand, if I try to bending load, apply the bending load which is parallel to the other axis which is not a axis of symmetry, I am applying the load parallel to this section or this segment, you see that it is rotating. So, this causes rotation of the cross section. So, this rotation comes up due to bending. I do not apply any twist, but then it rotates. I will show you another example which is going to show what is shear center about. So, consider this case. So, I have really like this, I have a section here, this is again made up of plastic, you see here this is this section which is like a C section. I have put some paper inside, that is all. So, it does not have any stiffness. Now, therefore, this is one of the axis of symmetry, and this is the other axis which is not a symmetric axis. Okay. So, now I put a load there. If I put a load there on the cross section, you see it is twisting, it is twisting. I put a load there, at this point it gets rotated. But if I shift the point of loading parallel to this wave, then you see it does not rotate. So, my plane of loading, which is this plane, so that plane of loading is parallel to this side, and this plane intersects the axis, this axis at a point, that is called the shear center of the cross section. So, intersection of the loading plane with the bending axis is called the shear center. So, this is the bending axis by this load, and therefore, intersection of the loading plane with the axis of bending is the shear center of the cross section. So, it lies outside the cross section, you see, it is somewhere here, it is at a distance. So, this is for this section which has one axis of symmetry. Let us look into another example. Look at this example. Here this is like a L section. So, this L section, now we do not have any axis of symmetry here. Now, if I put the loading parallel to this edge, let us say I put this load there, you see these sections rotate, it rotates, and if I shift the point, see here the rotation has reduced. So, therefore, if you come to this corner, it does not rotate. Similarly, if I now put the load parallel to this side, you see, if I put the load, it has twisted, you see, it has twisted. But if I put the load here, it does not twist. I think let me show it again. So, you see, it gets twisted. But then, if I put the load very close to the corner, you see, it is close to the corner parallel to this, it does not get rotated. So, this is the phenomena. So, I will show again, you see, it gets rotated, but then the moment I put the load very close to the corner, this one, you see, or rather let me put it this way, you see, here the rotation is not very significant, like this. So, maybe you can see this thing better here, maybe here it may be better. See, I put the load there, it gets rotated, but then if I put the load there, it does not get rotated. Similarly, if I put the load here, it gets rotated, but then if I put the load there, it does not get rotated. So, that is the point which will be related to shear center. So, let us try to do some calculations on this determination or they are locating the shear center. How do we go about it? So, let us get back to our sections, C section. So, we have a beam with C section here. So, this is the beam we have. Now, what we have shown you is that the axes of the cross section are as follows. This is your y, this is z axis, right. Now, if we put a load parallel to this y x plane, so parallel to y x plane, let us say that we put a load here somewhere there, you just think of it that we have put some member, welded some member and then we are putting a load there, then in that case this is going to be at a distance. So, this is the plane y x plane. So, this is x direction is here. So, this is y x plane and this load is acting at a distance of E z from this y z plane. So, if that is the case, you are going to have now shear force acting like this vertically up. So, that is the shear force V, and this shear force V for this case it certainly is equal to P. Now, because of this shear force, what you get now, that there will be a force acting due to the shear stresses acting on the flange. On this flange we will have some shear stress, which is shear force which is coming up, sum of the all shear stresses, let us say F1, or if you would like to write parallel to z axis, so therefore it is Fz. Similarly, the shear stress acting on this flange, it is going to be Fz. So, now if we consider the moment of this forces Fz, then I am going to get, if the height of the flange is equal to, let us say, h. So, from here to here, let us say it is h, then Fz into h is the moment which is clockwise if we look. And now, if I consider that load is acting at this point, then I will not have any moment produced by this force P. On the other hand, if I shift it here, it will produce a moment about this plane which is going to be P into Ez. So, therefore, that can keep a balance. So, there is a unbalanced moment, and to keep it in balance we must shift the loading point away from this location, and therefore, since V equal to P, we can write V into Ez, and that is equal to P into Ez. So, this load must act at a distance Ez which is not equal to 0. So, this Ez not equal to 0. Now, if you consider the plane containing the load which is parallel to a plane xy plane, that is going to intersect the z axis at a distance here. So, it is going to intersect here, and this distance is again Ez, and this is known as the shear center of the cross section. Shear center. So, it is the intersection of loading plane with z axis is called the shear center. So, we will write this intersection of loading plane with z axis is called the shear center. You can imagine that if the cross section is not having any axis of symmetry. So, if you consider this cross section, so if I consider now loading acting parallel to this edge, we must have, if this is the CG cross CG of this section, then obviously I expect a distance of this plane of loading so as to keep the forces in moment in balance. Similarly, if I consider the force acting parallel to this leg, then I also expect a distance of the plane of loading from this, and therefore, in both the cases we are going to get some distance away from this CG. So, if these are the axis, let us say YZ, then when I have a load parallel to this leg, then I will have some location of the plane of loading with respect to CG which will intersect with Z axis, that will give us the location of shear center with respect to the that sort of loading. Similarly, if I consider loading in a plane parallel to this, I will have some distance away from the CG. So, therefore, those two will finally, you will find that in this case you are going to have this intersection point. So, this plane and this loading plane, they are going to intersect at this point. So, you must have, for complete balance, what you need is that this force, if it is to be balanced, we must have a loading plane passing through this type of location, and then if we have to keep the this force in balance when I am applying the load, then I must have this as the plane of the loading. So, I repeat again, when I am trying to curve bending by applying load on this or load parallel to this leg, then I must keep the balance of this force. So, therefore, it should pass through this line, loading plane must pass through this line. When I am applying the bending load parallel to this leg, then I must balance this force, therefore, the loading plane must pass through this line, and therefore, the intersection here will give the shear center for the cross section. So, here you will find for angle cross section, shear center is always located at the corner, and that is what we had shown here, that for this particular case, once more let us look into this, that herein you see that this is the cross section, which is not exactly right angle, unfortunately. Let us consider this one. So, this one you see here, if I apply the load, it does get twisted, but then if I apply the load, it does not get twisted to that extent. So, let me see, you see that I am applying the load, it gets twisted, but if I apply the load, it does not get twisted. Similarly, if I consider the load applied like this, it gets twisted, but then if I apply the load at the junction, it does not get twisted. So, therefore, this corner is the shear center for this cross section. So, now we will solve some problem to have further understanding of this one. So, let us consider example 1 on shear center. We have a cross section given here. The flanges are of dimension 60 millimeter, web is also of dimension 60 millimeter, and the wall thickness is 5 millimeter everywhere, and so therefore, this is 5 millimeter, and so also this is also 5 millimeter. Now, Iz for this cross section has already been calculated, and it is 50.7 into 10 to the power 4 millimeter raised to the power 4. So, what is needed here is that we have to calculate the shear position of the shear center. So, loading plane is parallel to y axis. So, therefore, V is acting like this, and therefore, the shear stresses will be oriented in the flanges like this. Now, let us first of all find out the shear force acting on this arm and also on this arm. Obviously, the magnitude of the shear force here and here they will be equal. So, if you want to calculate the shear force acting on this arm, let us consider a point at a distance of xi from this edge, and therefore, you remember that the shear force, shear stress at this point is going to be given by, if you consider tau, this tau is going to be V is the shear force multiplied by the moment, first moment of area of first moment of this area about the neutral axis. So, therefore, let us represent that by Q, first moment of this hatched area, VQ by thickness into Iz. So, therefore, that is the formula. This you have derived in the first course. Now, if I want to integrate, I have to integrate, let us consider this junction to be at a distance of 55 millimeter from this. So, therefore, the total force is going to be nothing but 0 to 55 VQ by BQ by TIZ into dA. So, if we consider this Q is of course this area, and now if I consider an elemental area dA, so this is T into d xi. So, that gives us the so that is equal to V by Iz 0 to 55, and it is of course T we can keep there 5 into xi. So, this area, this is 5 into xi, and its height is nothing but 30 minus 2.5, 27.5 d xi. I think this 5 into this is the area. So, therefore, we will have this also there, T is there. So, therefore, finally, this T cancels, and finally, what we are going to get this as V by I z 5 27.5, and integration of this thing will give us 55 square by 2, and so therefore, that is the force. Now, if we consider that the shear center is to be located somewhere at a distance of E z from the y axis, let us say this is E z, then we can write that moment of, so this, if this is V, this is also V. So, V into E z, that will counterbalance the moment due to the force acting on these two arms, and therefore, this is nothing but it is we can write F. So, this V by I z into 5 27.5 55 square by 2, and this height is nothing but 55. So, therefore, this is what is going to keep balance. So, the force F is acting on this arm like this F, and on this arm it is like this. So, therefore, they produce a moment which is counteracting with this moment, and therefore, we can now simplify. It gives us V into E z is equal to 0.41 V multiplied by 55. So, therefore, this is nothing but 41 V, and hence E z is equal to 22.5 millimeter. So, the plane of loading cannot be y plane, it must be at a distance of 22.5 millimeter from the y axis, then only the twisting of the cross section can be prevented. So, this is one example to show how we can go about calculating the position of the shear center of a section which has one axis of symmetry. Let us consider another example. So, this cross section is shown here. It is like T, and the orientation is like this, that you have one flange oriented vertically and this is another flange, but then this is the wave which is aligned with the z axis, and this AB and CD they are related. This is 3 times AB. So, therefore, 3 AB CD is equal to A, and this is equal to 3A and this is equal to A, and the distance of the two legs AB and CD is equal to A. Let us consider that this particular cross section is subjected to shear force like this. So, if it is subjected to shear force like this, then we are going to have shear stresses coming up. So, it will be like a parabolic distribution. So, we will have maximum magnitude of the shear stress coming up at the center, and it will reduce to 0 at the top edge. Similarly, it will reduce to 0 at the bottom edge, and on this side we are going to have again this also is going to be gradually reducing to 0 at the top edge, starting from maximum at the center. Same is the picture as we go to the bottom edge. So, let us consider that sum total of these forces is equal to V1 and sum total of the forces is equal to V2. Now, in this case it is obvious that we have this y axis is a it is not a axis of symmetry, but z axis is a axis of symmetry. So, the plane of the loading must be offset with respect to y axis so as to remove the twisting of the cross section under bending load. So, in order to do that, let us now consider the force V1 coming up on this arm AB. So, we consider a section or fiber at a distance of, let us say, xi 1 or rather xi, let us say, from the neutral fiber, and now we would like to consider the shear stresses at this level, which will be given by Vq by Ti z, that is the shear stress, and therefore, we can write now V1 to be integration of the shear stress, which is nothing but V by Ti z, and Q is nothing but A by 2 minus xi into T, that is the area, and its Cg is at a distance of half A by 2 plus xi, that is the Cg distance, and then we can consider that integration is equal to d xi. So, that is the area, and Vq into dA. So, we will also have one T coming here. So, finally, what we find here is that we will have the integration limits are minus A by 2 to plus A by 2. So, please note that this is the shear V by T I z, this is nothing but Q is from here to this expression, and this is dA. So, now if I just substitute here, so one T will cancel, so we will have V I z, it is half, and this is a form A square by 4 minus xi square, it is easily integrable. So, we will have A square by 4 into A minus integration of xi square is 1/3 2A cube by 8. So, that is integration, and it gives us value equal to V by 12 A cube T into I z. So, that is the shear force acting on the leg AB. Similarly, V2 can be calculated. So, you can take again a fiber at a distance of xi and take the Q corresponding to this portion, and hence you can calculate the sum total of the forces, which is V2. V2 is equal to minus 1.5A to 1.5A, and this is V t square 2 t I z, and it is 1.5 A square minus xi square d xi. So, it is simply we try to replicate that form, and then once you calculate this, it comes out to be V t two I z 2.25 A square into 3A minus 1/3 to 1.5 A cube, which on simplification becomes 27 V A cube T by 12 I z. So, we have seen the shear force acting on the two vertical arms, V1 on the left and V2 on the right, and obviously the external force is going to be balanced by sum of this V1 and V2. So, we can now write that schematically we have V1, this is the cross section schematically, and we have V1 acting here and V2 acting there, and as I said that our external force is acting vertically up, and therefore, it is acting on the vertical plane, and so this sum total of these two will be passing through somewhere here, and we must see that the external loading is also passing through the same point, or it must act on a plane which must pass through the same point. So, if the external loading is acting on a plane, let us say somewhat like this is the external load, then in that case let us consider that it is acting at a distance of z1 from the left arm, then we must see that the moment is balanced. First of all, we have V1 plus V2 is equal to P, which is nothing but total shear force, and now we must see the balance, moment balance also. So, therefore, we can now write, if I take the moment about this point, we are going to have V2 into A, this distance is A, is equal to V into Z1. Now, we have already got V2 values. V2 we have already obtained as 27 VA cube T by 12 by Z. So, therefore, this Z1 is equal to 27 V A cube T by 12 I Z into A by V, and this gives us 27 A4 T by 12 I Z, and I Z for this cross section is approximately equal to 7 by 3 A cube by T, A cube into T, and therefore, this Z1 comes out as 27 by 28 A. So, it means that the plane of the loading must pass through a point which is closer to the longer arm, so that the moment balance will be there. So, we have now got two cases, and we have seen that the location of the shear center needed nothing other than the orientation of the external load, and we have been able to find out the location of the shear center. So, the shear center is a property of the cross section. Given the orientation of the loading, it is a property of the cross section. That is why always we try to find out the location of the shear center without any consideration to the loading point. We simply consider what is the orientation of the loading and try to calculate it. Now, I will try to consider one more example, and I will show you that the calculation can be done in a little simpler fashion. So, let us consider this example. So, it is a section which is like C, but then we have some flanges also on the other side. It is not exactly C type section, and wall thickness everywhere is 10 millimeter, and this height is 110, and this is 60, and this flange length is equal to 20 millimeter. The CG of the cross section is somewhere here, and this Z axis is an axis of symmetry. Y is really the axis which is not a symmetric axis, and therefore, loading in planes parallel to Y will give rise to, or will have to be offset with respect to the CG, so as to eliminate the twisting of the section. So, we would be interested in trying to find out the location of the shear center when the loading is on plane parallel to Y. So, we have the shear force acting like this. Now, for this section you must first of all find out the shear stress directions, which is critical. It may not be that obvious. So, if shear force is acting like this, then in that case the wave shear stresses are going to be, it is going to have maximum value there, and it is going to reduce as we go away from the center point, and we expect the flange stresses to be maximum at this junction, and it will reduce as we move away from it. So, therefore, this is how it will become 0 there, and exactly similar picture will exist here, it is 0 there. Now, about this flange, it is again the shear flow is going to have shear stress is going to have maximum value here, and it will be 0 there, and on this flange it is going to have maximum value at this point, and then it will be 0 there. So, here you have a picture is shear flow, that is why shear flow is very important. The force V is acting, therefore, the shear flow must be like this, and for this also it has got to follow that it should be in this direction. That flow analogy is very, very important. So, you have the total flow coming here, it is getting branched out into this, and here in this flow is coming, this flow is coming, and this is also coming, this gets added up to this flow. So, that shear flow analogy is very useful in these applications. Now, the sum total of the shear force on this flange is going to be, let us say, V1, and since it is symmetric, I would also have sum total of the force coming up on this is V1. Obviously, this will be directed in the to the left, and this will be directed to the right. And on the other hand, let us consider the sum total of the force that comes up from this flange is equal to V2, it is directed to the left, and the sum total of the force which will come up from here, it is again going to be V2, but it is going to be directed to the right. Now, the distribution of the shear stress is going to be linear. I think you remember that this shear stress is going to vary linearly on the flange like this, and same is the picture here. So, also it is going to be linear, and on the wave it is going to be parabolic. So, let us now find out what is the maximum shear stress. So, if you consider this particular point here, which is at a distance of 50 from this edge. So, the maximum shear stress, this one, if we indicate this thing by tau max 1, then this tau max 1 is equal to V, Q is nothing but first moment of this area about the z axis, that area is nothing but 50 into 10, and its distance is nothing but it is 45 plus 5 is again 50. So, this is nothing but Q, and divided by thickness of the wall by I z. So, this gives us the value, some value, and the average value which is going to be half of it. So, therefore, let us say this is the average value of the shear stress on this flange, and let us say that this is tau average is equal to, it is half of this tau maximum, and it comes out to be 1250 V by I z, because it is 2500 V by I z, half of that is 1250 V by I z. Now, let us consider this one, this sum, here it is again it is linear. So, I will draw it here, that this variation is again linear, it is like this. This is, let us say, tau max 2. So, tau max 2 is equal to, it is nothing but V multiplied by Q of this divided by T into I z. So, therefore, V area first moment is 20 into 10 and it is at a distance of 20, wall thickness is 10 IZ, and therefore, this is 4000, it is 400 V by IZ, and therefore, the average value toy AV2, that is the average here, that average is equal to 200 V by IZ. So, we can now easily calculate the total shear force V1, which is nothing but average shear force multiplied by the total area, which is 50 into 50 is this distance and into 10. So, therefore, we can now write that the total force V1 is nothing but 50 into 10 multiplied by the average shear stress, which is V by 1250 V by IZ. Similarly, V2, the total of the force here V2 is nothing but 200, because this 200 is 20 into 10 is 200 is the area multiplied by 200 V by IZ. So, that gives us the two shear forces. Now, we have to see that the moment produced by V1 and V2 are balanced by having an offset location of the loading plane. So, what we have to do now, this V1 acting on this flange and on this flange they are producing a moment which is clockwise, and this V2 is going to produce a moment which is anti-clockwise. So, net we are going to have a clockwise moment, and if we have to balance that, our loading plane must be somewhere this side with respect to CG, and therefore, we have to calculate that distance Ez. So, now I can write the balance equation V total shear force multiplied by Ez is equal to V1, and this distance from this to this middle, it is nothing but 100. So, that is the moment, and V2 is the other force, and here the distance is, it is again from here to here is 40. So, therefore, that is the equation to calculate the distance Ez of the loading plane, and if you substitute these values of V1 and V2 here, on simplification you get Ez equal to 35.8 millimeter. So, this is how you can find out in a little simpler fashion the shear center. Now, once again I want to reinforce the point that the shear center is a very special location of the cross section, and that point must be noted while trying to consider the loading in bending of the beam. Now, how do you go about finding out the shear center in the case of section angle section? That is something I want you to reflect upon. So, how do you find out the, say let us consider this example. Example 4. Now, we are trying to talk about section of this type. Let us say that these are the two axes here, which are both are unsymmetric for the cross section. Now, if I am trying to apply a load, let us say I will apply a load parallel to V1, then in that case I have to see that the shear forces which are going to come up here, it must be actually in balance. So, therefore, what we try to do here in actually see that it is going to give rise to force here on this leg and force here on this leg. So, therefore, let us say that the shear force here is F1 and F2. So, this F1 and F2 would have a intersection point there, and if this force passes through this intersection point, then you will avoid twisting of the cross section. So, let us look at this demonstration again. So, what I said that this is my cross section, this is my cross section. So, I have this is this and the other arm is this one. So, if I am trying to apply a load parallel to this, it is twisted, but if I make to pass it through this point, it does not get twisted. So, therefore, we must actually see that this load passes through the point of intersection here. Similarly, if you are now trying to consider, let us the loading plane is like this, which is parallel to the other arm. So, then in that case again I am going to get forces like this F2 and F1, of course, the magnitudes will be different, and if I have to balance the moment, I must see that this line of action passes through again through the common point. Now, let us look at this. So, what I am trying to say now, I am applying force parallel to this. So, therefore, I am applying force parallel to this, you see it gets twisted, but then if I apply the force which is close to that intersection point, it does not get twisted. Look, this is twisted, but if I apply the force through that point, it does not get twisted. So, therefore, for such L sections always you will find that the intersection point is the shear center. Even if you have a section like this, if you have a section like this, here again if you have a vertical force acting like this, the shear forces is going to act this way, and then their intersection point is here, and you will find that the shear center is going to be passing through this point. So, this I think is it can be easily established. See that this is the section, now we are trying to keep it at an angle. So, I am keeping it at an angle, and therefore, now if I put the load passing through this point, it does not get twisted, its orientation remains, that is it. So, you can consider solving examples by considering problems which are given in L.S. Srinath, Advanced Strength of Material.